Okay, in this video, we want to talk about a singular point of a differential equation. Singular point of a differential equation. In the previous video, we talked about a regular point of a differential equation where I told you how to get, okay, to recap, if we have that this equation, if you have y prime plus p of x, y prime plus q of x, y is equal to 0. I told you that if p of x is not equal to infinity and q of x is not equal to infinity at a particular point, say let's say at x equal to a, okay, if at x equal to a, that p of x and q of x are not equal to infinity, that means that they are analytic. You can visit the video to understand it better. So if it is not equal to infinity, we conclude that what? That x equal to a is a regular point of this equation. But if they are equal to infinity, we say that it is a singular point of this differential equation. So if one of them is equal to infinity, we don't even need to check all of them. If you find out that p of x or this one or even the two of them, either of them is equal to infinity, we conclude that what? That point is a singular point of this differential equation. Okay? So we are talking about singular points now. So we will say that if p1 of x, p of x or q of x is equal to infinity. In fact, if one of p of x or q of x is equal to infinity, if p of x is equal to infinity or q of x is equal to infinity at x equal to a, then we conclude that x equal to a is a singular point, is a singular point of the differential equation. Okay. All right. Now, singular point is of two types. We have the regular singular point and the irregular singular point. Regular singular point. Okay. So don't forget that if they are equal to infinity, if they are not equal to infinity, it becomes an ordinary point. Sorry, I don't know if I said regular that time or ordinary. So it's supposed to be ordinary point. Go and watch the first video. Okay, this one is the second video. Now, how do you know whether it is a regular singular point or an irregular singular point? You should note something for me, that analytic plus analytic again, okay, plus not analytic is what we call the regular singular point. Let me explain what I mean by that. Now, first of all, we have noticed that x equal to a is a singular point. It must be a singular point first before we now check if it is a regular singular point or not. So we are going to check p1 of x, and it has a formula. p1 of x is equal to x minus that a, okay, then p of x. And then q1 of x is equal to x minus a again, all squared q of x. Now, if you use x minus a to multiply your p of x and use x minus a all squared to multiply your q of x, and then you discover that as x equal to a, that p1 of x is not equal to infinity, and q1 of x is still not equal to infinity, then we will now conclude. We conclude that x equal to a is a regular singular point of the differential equation. So first of all, when we check x equal to a, when we put x equal to a here, we discover that p of x is equal to infinity, or q of x is equal to infinity, or even the both of them are equal to infinity. That means that they are analytic. That's why I said, okay, they are not analytic. Sorry, here should be not. Okay, and here should be analytic. So that's why I said not analytic plus analytic should give you regular singular point. So if they are not analytic, means that they are equal to infinity. If P of S and Q of S are not analytic, that means at this point, we say that this point is a singular point. And then if we now do this thing and find out that they are now, what am I saying? That they are now analytic. How are they analytic? Because this and this is not equal to infinity. Remember, if they are equal to infinity, they are analytic. At the beginning, they are equal to infinity. Then in the second stage, they are no longer equal to infinity again. That means in the first time, they are not analytic. In the second time, they are now analytic. We now call that point regular singular point. But if we discover that S equal to A, if we discover that at S equal to A, that P1 of X is still equal to infinity, and the Q1 of X and Q1 of X is still equal to what? Infinity. That means not analytic. That is P1 of X and the Q1 of X, or even one of them, are not analytic. Then we now conclude that therefore X equal to A is an irregular singular point of the differential equation. So that was why I said in conclusion, or in summary, that if you have that P of X is not analytic, and then you check again and it's still not analytic, we say that it is what? An irregular singular point. So note that not analytic and analytic will give you regular singular point, but not analytic and not analytic again will give you irregular singular point. So in this video, we are going to be solving the power series solution of a regular singular point of a differential equation. But for irregular singular point is above this scope, so I'm not going to be solving that. Okay, you can learn that one yourself, but I'm going to be solving the power series solution, power series solution of a regular singular point of differential equation. Regular singular point of a differential equation. Okay, so let's have a question. Okay, before we even solve the power series, let us have an example to what I'm saying, so that we'll know how to find the regular singular point of a differential equation. So the first example here, example 1. Example 1 said find the regular singular points of the differential equation 2x squared y prime prime plus 3x y prime plus x squared minus 4y is equal to 0. Okay. So from here, we have to make y prime prime subject. Okay, by dividing through by 2x squared. So we say divide through by 2x squared. So we are going to have y prime prime plus 3 over 2x, because one of the x above, we cancel one of the x here, y prime plus x squared minus 4 all over 2x squared y is equal to 0. Okay, so that means that our P of x, will now be equal to 3 over 2x, and then our Q of x will now be equal to x squared minus 4 over 2x squared. Now obviously at 0, this is not analytic. In fact, for you to check the point where it is not analytic, In fact, if you want to check the singular point first, you know that you first of all check the singular point before the regular singular point. For us to check the singular point, you just equate this one to 0. This one at the denominator. You equate it. In fact, the coefficient of this is what we equate to 0. So we say that 2x squared is equal to 0. So finally, x squared will be equal to what? 0, and then x is equal to 0. So it's obviously that when x is equal to 0, that this is going to be infinity, and this one is going to be infinity. So at x equal to 0, that x equal to 0 is what? A singular point of this differential equation. It's very obvious. So we'll tell them that x equal to 0 is a singular point of the differential equation. It's obvious because if you put it here, if you put p of 0, put in 0, p of 0, I'm going to have 3 over 2 into 0, which is giving me infinity. So this is not analytic. So at q of 0, in fact, when one of them is not analytic, it becomes a singular point. But let me check the other one. If you check the other one, you have that x squared minus 4 all over 2 into 0. I'm still having what? Infinity here. So you see, obviously, that x equal to 0 is what? A singular point of the differential equation. So now let's know if it is now regular or irregular. How do you know? You get your p1 of x. p1 of x will now be equal to x minus that 0. Okay, that's 0. X minus that 0. Then you have p of x, which will give you x minus 0 is x. So, and my p of x is 3 over 2x. So if x take care of x, I'm having what? 3 over 2. So p1 of 0 is still the same 3 over 2 because there is nothing I'm substituting. Okay, and then you see that this thing is not equal to what? Infinity. So p1 of x, in fact, p of x is analytic. So it's analytic. So the next thing we check is q1 of x, which is equal to what? X minus the same point 0. X minus the same point 0 all squared, then q of x, which is what? This and this will give you x squared here into, this one gave me x squared minus 4 all over 2x squared. So if x squared cancel x squared, I am left with x squared minus 4 all over 2. So q1 of that same point 0 will give you 0 squared minus 4 all over 2, which is giving me minus 4 over 2, which is what? Minus 2. And minus 2 is not equal to what? Infinity. So therefore, x equal to 0 is a regular singular point of the differential equation. So write it for me. That x equal to 0 is a regular singular point of this differential equation. So now let's look for the one that is now an irregular singular point of a differential equation. Let's take one more example.